Spinor. See, let's see what does the Clifford algebra have to do with the Lorentz group. See, there is a commutation relation of two gamma mu's, and this commutation relation gives us the 4 by 4 matrices, this matrices S rho sigma, and definitely there are few properties of this S matrices with the gamma. It is a definition, and the one property is this: S mu nu and gamma rho is equal to gamma mu eta nu rho minus gamma nu eta rho mu. Okay, and we can prove it very easily, okay, from the properties of the gamma matrices. And similarly, if we represent this gamma matrix, this S mu nu matrices from a representation of the Lorentz algebra, so we can use and we can write down the property in this way. The same Lorentz algebra properties. Whatever the properties of the M in the previous video, the same Lorentz algebra. Because the relation is very lengthy, that's why I am not writing the relation. Okay, and so on. And we can prove it very easily. So this S mu nu are 4 by 4 matrices. 4 by 4 matrices. Because gamma mu are 4 by 4 matrices. Okay, the reason is because gamma mu are 4 by 4 matrices. So far we have not given any index name to the rows and the column of these matrices. Okay, and we can call them for alpha, beta is equal to 1, 2, 3, 4. Okay, so we need a field for the matrices S mu nu. Okay, alpha, beta to act upon. We introduce the dirac spinor field psi alpha. Dirac spinor field, an object with a 4 complex component, alpha is 1, 2, 3, 4. So under the Lorentz transformation, we have psi alpha x is S lambda alpha beta psi beta lambda minus x. Let's say it's a 22 equation. It's just a name. You can put it any name to the equation. Okay, you should not ask where is the 20 and 21. I'm just putting it randomly. This lambda is usual definition, exponential half omega rho sigma m rho sigma, and this S is again exponential half omega rho sigma, not m, it's because it's related to S, so it is S rho sigma. Okay, although the basis of generators for the Lorentz generators are m, and this generators are for a Spinor generator are S. Both are different. We use the same 6th number, this omega rho sigma, in both lambda and S lambda. This ensures that we are doing the same Lorentz transformation on x and psi. Note that we denote both the generators S rho sigma and full Lorentz transformation as S lambda, as a S. To avoid confusion, the latter will always come with a square bracket. Okay, so both lambda and S lambda are 4 by 4 matrices. So how can we be sure that the Spinor representation is something new and is not equivalent to the familiar usual representation gamma mu nu? Okay, to see that the two representations are truly different, let's look at some specific transformation. Okay, what are those transformations? One is the rotation. See, Suppose Sij. So Sij is this, half 0 sigma I. It is from the definition. I am writing it from the definition. 0 minus sigma j 0, which is equal to iota upon 2 epsilon I j k sigma k 0 0 sigma k. Okay, I not equal to j. If we write the rotation parameter, this omega ij as minus epsilon I j k and maybe rho k, we mean that this omega 1 2 is equal to minus rho cube. Then the rotational matrix, very easily you can write down, it is S lambda is equal to exponential half omega rho sigma S rho sigma, okay, which is equal to exponential iota phi dot sigma upon 2, similarly iota phi dot sigma upon 2 0 0. Okay, where we need to remember that this omega is antisymmetric. Okay, and when following factors of 2, consider now rotation by 2 pi. Okay, say x3 axis, this achieve this phi is equal to 0 0 2 pi. Okay, after the rotation. So the spinal rotation, you can see that we will achieve this, because it's a 2 pi rotation. This S is this E iota pi, not 2 pi, and it will reverse the sign, it will give you minus 1. Okay, so 2 pi rotation just rotates psi alpha as a minus psi alpha. Okay, question 20, which is definitely not what happens to vector. To check that we have not been cheating with the factor of 2, you can check the same transformation rule with the gamma matrices. In the gamma matrices, you will find out that the answer of gamma will come out to the 1 after the 2 pi rotation. Okay, so S lambda is definitely a different representation from the familiar vector representation of the lambda. So S lambda is different from the lambda representation. Okay, it is a spinal representation, it is a general Lorentz representation. Okay, that is the main difference. Okay, and after that we will discuss and we will tell you about how we can construct an action with the help of this thing, and we will move towards the Dirac equation. Okay, thank you.